This is another LLM paper. I know I've been covering a lot of LLM papers, but I mean, this is kind of where we're at right now. But basically, this is another linear transformer paper, but this one is really interesting in how they do it. It's different from a lot of other things. They use a meta-learning technique, and meta-learning is basically learning to learn. So the model teaches itself how to learn in some area. Usually you have an outer loop and an inner loop for that. It's a really unique thing that they do, at least from what I've seen. So I wanted to cover it. Yeah, so learning to learn at test time. That's the name of the paper, RNNs with expressive hidden states. So another linear transformer, or an RNN, because all linear transformers are basically RNNs. So let's go over this. Basically, we all know the problem with transformers. If I have my transformer, we have the softmax of our queries, keys transpose times our values. And the reason this is bad is because this is quadratic in terms of the sequence length. So as the sequence length grows, you have your matrix here, and as it grows quadratically, and this matrix grows quadratically in terms of memory. And this is your attention equals QKT matrix. And the reason is because you have your softmax right here, and the softmax here forces you to compute this QKT matrix. And you have tricks to go around this, but linear attention mechanisms basically, well, some of them will remove the softmax and try to replace it. Others will try to develop a completely new method. And this falls into the latter, where it tries to develop a completely new method, like an RNN, to replace this here. So be as expressive, yet be linear in terms of memory. Now, for an RNN, the main issue with an RNN is it's not expressive enough, but also as you increase the sequence length, the RNN starts to fade off. And they actually have a diagram here showing that. So normal RNNs, like, you basically have your hidden state, and every time you have a token, so this is your hidden state, and every time you have a token, say xt, maybe we'll do the simplest hidden state here, and we'll just add it. So this will be ht plus 1. So you just add the token. Now, the problem with that is as you keep on adding tokens, this is basically going to diverge and go to infinity. And this basically causes a divergence problem, where you can't, like, everything basically becomes the same. The hidden state becomes useless. You can't have any information if all the information's the same. So as you keep on adding tokens, you need to have this compression task so that you only keep the information you want while you remove the information you don't need anymore. Now, this is a problem because as you increase the sequence length, there needs to be more and more information in this hidden state. Intuitively, if I were to give you more and more words, more and more context, you'd be able to answer whatever question better. So if I give you more context, you should be able to answer a question better if I ask you. However, in an RNN, since all the contexts go into this hidden state, it actually starts to fade off as you give it more context. So as the token index increases, as we give it more context, for the best RNN we currently have, Mamba, the perplexity starts to fade off and it starts to kind of level off right here, where the model doesn't continue doing better as the token index increases. Now with attention, the hidden state is every single key and every single value if you use KV cache. So it basically has context of everything because it can look at everything whenever it wants, as opposed to RNNs where it has to store everything in the hidden state. So we want something as expressive as softmax, or as softmax attention, while we want something as fast and as memory efficient as an RNN. And RNNs are fast during inference, not during training, but yeah. So that's the idea. So let's just start with a basic RNN, and then we'll construct this learning to learn method from there. So like I said, the basic idea with an RNN is we're going to compress things with a hidden state. So let's just call H0. We'll just make this some vector. We'll make the update equal to the sigmoid of, say, theta h of ht minus 1. So this is just going to tell us how much of our hidden state we're going to keep, plus theta maybe x of xt. So basically our hidden state is going to be composed of the current hidden state through a projection plus our next tokens. But this is being sent through a sigmoid, and the problem with that is you keep on compressing this information more and more. So you need to store more information, yet since sigmoid is between 0 and 1, you can only store so much information in this domain here. Now if we remove it, then this will diverge because we keep on adding more and more x's. This will eventually become a massive sum, I don't know, to some big T of xt, and obviously this is going to diverge. So instead, and this also has an output, so zt is equal to, say, theta, I'll just call this a of ht plus theta b of xt. So z is a function, our output is a function of the hidden state and the input if you so desire. So this is the RNN, and basically if we keep sigmoid, it keeps it from being expressive, but if we remove sigmoid, it keeps it from actually doing anything useful because it'll diverge and our loss will not work. Like it'll just kill the model. So what we want to do is we want to compress this hidden state somehow, but we want to compress it such that it's still expressive. So what they do is they basically have this meta learning task. So what we're going to have is we're going to have our outer layer here. So our outer layer is going to be like this is a normal transformer. Like if this was just a transformer, this is our text. xt, maybe this is the cat, and we want to predict the next word. And this will just predict the word, or the cat sat. And this will just predict the next word, and we train it to predict one off. So given the, we want it to predict cat, and given the cat, we want to predict sat. So this is just our normal log likelihood, perplexity, or loss. This is just normal loss. And this is going to be called the outer layer. Now our inner layer is going to be somewhere in our transformer. So in our for the transformer task. So for the transformer task, we have these inner layers here. So self-attention, and then you have your feed-forward layer. Now, what if we take this inner part and we kind of replace it with like an RNN? So we have an RNN here. And we basically are going to use this to model our sequence. And other things have done this. Like Mamba basically replaces attention, replaces attention with like an RNN. But the idea here is we're going to have a loss function. So loss function here, which basically optimizes all the parameters around this. So we have our layer norm here, we have our feed forward here, another layer norm. We're going to have a loss function that optimizes all this. And in the inner layer here, we're basically going to have something that we're going to have this loss function. And this loss function is going to tell the model how to update its hidden state. And we're basically going to have our outer layer kind of learn this loss function here. And this is the learning to learn part. We have an outer layer that's just learning the main task, and part of learning the main task is learning this loss function, which will be used in our case to update the hidden state from, instead of using this here, we're going to have this loss function. We're going to utilize this learned loss function to update it. So how do we actually, like, what's going to be our update rule? And let's actually formalize this instead of just saying we're going to learn this here. So I showed the RNN thing up here. The way it's formalized is very similar, but basically we're going to have a bunch of RNN layers that we're going to be optimizing, and we're going to have an inner loss function to update those hidden states. If I go down here, we basically are going to have, let me remove this. So WT is going to be our hidden state. So we have some hidden state at time t. And we want to at time t minus 1. And whenever we get a new token, we want to update that hidden state. and we want to update it by the gradient with respect to some loss function. And this loss function is going to be used to inform the model how to update this hidden state. And the way we're going to do that is by just taking the loss, the gradient of the loss with respect to the hidden state. Now, I want to note that this inner loss is not being used to optimize parameters. It's not being used to optimize like the feed-forward layers in the model where you project to queries, keys, and values, or the embedding layer. All this inner layer is doing is updating W, and it's updating W via normal gradient descent. If you look at this is normal gradient descent. We have our old weights. Like if you look at this in terms of the weight perspective, we have our old weights, we take the gradient with respect to the loss, and we update it via a step in the negative direction, such that we decrease the loss, and this is our learning rate. So we're basically taking a gradient descent step with respect to an arbitrary loss on these weights, where these weights are not actual weights, but rather our hidden state. So this is our update rule from our hidden state t-1 to our hidden state t. So what's this loss function? Well, our loss function is going to be a reconstruction loss. So let xt be a token, and let x tilde t be a corrupted token. What we're going to do is we're going to say we have this function here, and for now the function is going to be arbitrary. And what this function is going to do is it's going to take in the hidden state, so it's going to take in whatever we have at our current time step. So basically all the previous information, so the cat, and then if it needs to predict sat. So all the previous information, the current token, and it's going to take the previous information and the current information, and it's going to try to reconstruct the token. Note that this is the inner loss. So this loss function doesn't make sense for the actual task, but what we want this loss to do is to basically tell us what tokens are more useful than others. So this loss function is just a reconstruction loss. This is our input token, this is the corrupted input token, and this here is the reconstructed input token using some function f, which is going to be like a learnable neural network, and our past hidden state. And this is our loss. So we basically give it a token, we get the loss from the token, and we use that loss to update our hidden state here. And this is just the gradient. So normal gradient descent step, except it's with respect to the hidden state. It's weird at first, but it makes a lot of sense whenever we look at this. So the task is a reconstruction loss, and we're taking the gradient of the reconstruction loss with respect to the weights, or rather with respect to the hidden state. And kind of what this means is that the tokens that make W learn a lot will have more impact on W. And if they have more impact on W, then that should update W more. So, or rather, that is, tokens that are harder to reconstruct, so tokens that are difficult to reconstruct, basically probably have more information because they're harder to reconstruct. And that'll update our hidden state more because the gradient will be larger. So whenever we have a large gradient with respect to this reconstruction loss for this single token, it'll update our hidden state more. And if we have a smaller magnitude for our gradient, it'll update our hidden state less. So more important tokens with higher magnitudes will be added to the hidden state more, while less important tokens will not be added. Now our update rule is right here, or our output rule is right here, and it's just getting the output. It's also a reconstruction loss, but or also just the reconstruction model that we have down here, but we'll get to that later. I drew out a diagram over here. Hopefully this makes it easier to see. So actually I'll get to this in a second. So after the meta learning part. So basically this is the idea. We have this gradient that we're going to be using to update our hidden state rather than a manual rule. Now what we need to do is what we want the model to learn this function here, this loss function here. We know it's going to be a reconstruction loss. We're going to impose that because the authors believe that that's a good task, and it obviously is because this model works quite well. But we want the model to learn how, like what, we want the model to learn this loss function somehow. So if we go down here, we can see how they do that. So basically, they relate this to transformers a little bit by making these query keys and value projections, but like it doesn't, there's an equivalent if you make them query key and value projections, but that's kind of besides the point. Let me erase this mess. Basically, what we're going to do is we're going to take our loss function here. This is the reconstruction loss function, and we're going to make it such that the model has to learn this reconstruction. But what exactly are we going to reconstruct? Or what information do we want it to reconstruct, and how do we want it to do that? The way they do that is they make the reconstruction learnable. So we have our token here. Our token is going to be in dimension D. And what they do is they have these down projections that they learn using these theta parameters. So this may be, I don't know, E, which is some dimensionality less than D. So what they do is they down project the token, and we want the model to, rather this inner model, to learn how to reconstruct this down projected token. Now we're not going to up project the token, rather we're going to down project the token twice. So one down projection is going to be here using the keys, and our inner function is going to learn how to down project, and our other projection here is going to be used to tell the model what we want it to reconstruct. And this will give us our loss. Now, this seems weird. You may think, oh, like if we just do this and the model's probably going to collapse, like it's going to make this task super easy. So the reason it's not is because we have these two loops optimizing. We don't have one loop, we have two. So thetas are our outer loop. Our model is learning the negative log likelihood, so just predicting the next word, and all it cares about is I want to optimize these theta parameters such that I don't care what this inner function is doing. I just care that it gives me a good representation that I can then use for my negative log likelihood prediction. So it isn't going to optimize these such that this loss is optimized. So these here are going to be optimized only for the negative log likelihood task, not for the reconstruction task. Now, let's swap to the inner model. The inner model is optimizing W. So it doesn't optimize these down projections here, meaning that they aren't going to collapse because it's like it wants to do this reconstruction task, yet it can't optimize these theta parameters here. It can only optimize the hidden state W. So it isn't going to collapse because it can only worry about how it reconstructs this. It can't look at the label here. So this is how we're going to learn it. This is how we're going to learn our loss. We're just going to down project our input twice. One time so that we give this down projected token to the model to reconstruct, and a second time to tell the model for this label. And intuitively, this is the outer loop model basically saying, how do I want the inner loop model to learn such that it gives me a good output representation of these tokens. So I think that's really cool. I think this part's really cool, how it doesn't collapse because of the way you train it. Now, the output has to be changed a little bit. So since we down project the tokens, we have this down projected output here, which is in some dimension E less than D. I'm just calling it E. But we want a token of dimension D. So what we're going to do is we're going to down project X a third time. So this gives you a third projection that the outer model is going to learn. And we're basically going to use our reconstruction model here to or some other function to just learn the output projection. So that's all we're doing. So yeah, basically this is the idea. And yeah, here is a diagram I kind of showed I put together to kind of simplify this a little bit. It looks bad, but let me explain it. So this is our input token here at time t. this is our hidden state here at time t-1. And what we do is we project this using our outer loop parameters, our theta parameters, to our queries, keys, values. It's actually written here as k, v, and q. So the first thing we do is, now that we have these down projections here, so this will be of dimension d, this will be of dimension e less than d, so that it learns to reconstruct stuff. This will be our loss here. So we basically take the loss of some function, we'll get to that later, and the values. I guess that should be a minus sign here. So this is just our reconstruction loss. We then take the gradient with respect to the weights here. And these weights it's just our hidden state. And we then do the update here. So the update using the gradients that I showed earlier. And once we have WT, we can we can do this output projection here using the queries and our current hidden state here. So this is the idea here. It's just a normal RNN basically, except you have this learned loss function here. Now, if we look at this, this obviously has a problem, and or I guess it's not too obvious, but it has a problem, and the problem is with a normal RNN. You cannot parallelize a normal RNN, which is annoying because you cannot utilize the GPU very well. You have to do this sequential sum, and sequential sums are slow, forward and backward. You don't want to do that. The reason transformers are so nice is because you can do a matrix multiplication. 3 matrix multiplications and you're done. With this formulation right now, we have to do a ton of sums, and we have to do a normal RNN update rule. And doing that is not favorable at all. So they developed this idea to make it parallelizable. So let's start with what we currently have. So we currently have this update rule here. Basically, w at time t is going to be equal to w at time 0 times the learning rate, or minus the learning rate, times the sum of all the gradients. Now, this doesn't look bad, except this GS is dependent upon the previous gradient and the previous hidden state. So you can't just compute these in parallel, obviously, because we're doing gradient descent. You can't compute them in parallel. You have to compute them sequentially. Now, what they do is they basically say that you can compute these in a batch. So let me draw that out. Yes, pull it out this way. So basically, you can compute these in a batch. Let's just look at these through 3 different views. So the idea is we have a bunch of tokens, and we're going to throw these tokens through an RNN. And our current way to do that is by taking the first token, throwing it through the RNN, computing a hidden state. Taking the next token, throwing it through the model, getting another hidden state. Taking another token, and then getting another hidden state. So this is our sequential process. Now, this basically requires H0, H1, and H2. They call it W in the paper. I'm going to call it H because I personally think it's more intuitive. And this requires our sequential operation. Now, what we can do is we can say, well, what if we base this token, and this token? What if instead we base them on basically hidden state 0 only? So what we're going to do is we're going to say, okay, these 3 tokens here are going to be based off H0. H0 here. And we're going to say this first token is going to compute H1 using the hidden state H0. This one is going to compute H2 using hidden state 0. And this one's going to compute H3 using hidden state 0. Now this doesn't make much sense because hidden state 2 depends on hidden state 1 and hidden state 3 depends on hidden state 2. So this is what they call a batch update, and this is more like all 3 are hidden state 1. And if you add them together, you get hidden state 1 using this batch update rule. This is kind of like batch gradient descent in a way, where we take a batch of data, we basically compute multiple outputs for that batch, and we take the average, and we say that is going to be our update. Our update is going to be is batched usually. So then now that you have H1, you can process the second batch. So you would take this token here, you would compute a part of H2, this one would compute a part of H2, and this one would compute a part of H2. And then you sum these together along with you sum these together. This gives you your update step, and you update H again. So this is like normal gradient descent. Now there's a problem with this, and this is that we process more tokens, but you're effectively just doing a one-step update at a time. Like, this to us looks like multiple steps. Like, you're doing 3 update steps at a time, but you're actually pretty much doing 1 because this is a batch. It's not 3 sequential steps. So what they do is they say, well, what if instead we take H0 and we're going to use H0 to not update a sequential batch, but rather the first token in 2 or multiple batches. So let's check that out. So instead of using these 3 tokens, we're going to use this token and this token. So this will be a mini batch update, essentially. So that's what they call it. So H0 will be used to update this one. So this will give us H1, and this will give us H1. And both of these are H1 because this is going to be a... basically, these are 2 different sequences. So you can think of both of these as like, oh, they would actually be H1. While in our other method, these were treated as H1, yet this was H2 and this was H3. So intuitively, this should make more sense and it should work better. So you take both of these hidden states here and you add them together to get H1. So H1 is the combination of these. And then you look at the next tokens, and this would give you H2. So this will give you H2, and this would give you H2 using the H1. And then the third tokens would give you H3. So you can kind of see we're processing the tokens differently, in a different way. So I kind of drew it out over here as well. Basically, if we have 3 batches, we would process, and we're processing it in sequential order like this. You would process the first batch here for t equals 1, 2, and 3 at the same time, and then t equals 4, 5, 6 at the same time, and then 7, 8, 9, or 5, 6, 7 at the same time. While here you would process this token, and this token, while these 3 are different sequences at the same time. So different ways of doing it. They mention that the mini batch gradient descent method is better. Though they do note that this does have an issue down here. So it's faster because you can compute it in a batch. It's parallelizable, but it does have an issue. It does have this trade-off. So as you increase the batch here, as the mini batch size increases, the perplexity increases as well. But as you increase it, it also has like the time to make this computation also goes down. So it's this trade-off. They pick a size of 16 because the perplexity increase isn't very high, while the time taken is much lower than if you were to just do a single batch at a time, or a batch size of 1 at a time. Now, they mention down here that there's this dual form here. Basically, it's just a way to compute things efficiently by reordering how you do the operations. And because you can compute the gradient operator, like you know what the gradient operator is beforehand, since it's an easy thing to compute. It's an easy gradient to compute. You can just model the gradient as a function rather than doing like backpropagation on it. You can just model it as a function. So this is like an efficient way of doing the computation mentioned above, where this is the output rule and this is the update rule. Basically just reordering these such that you don't have to compute like a D by D matrix. Rather, you just have to compute B by D matrices, which is nice. Theoretical equivalences. They basically show that this is equivalent to like linear attention, and they show down here that it's actually equivalent to self-attention, which is kind of cool. So if you're curious, go ahead and look at the proofs over here. I think they have it in the appendix as well, but it's kind of interesting that these are equivalent. Now let's go through the results. So let's look over here. If we look at the ablations that they do, they basically say, all right, we're going to start with the base model and we're going to start adding things. So the first thing they add is this learnable W0. And that's going to be learned using the outer model instead of the inner model. So learnable W0. Now, they mention here that learnable W0 hurts the performance slightly, so plus 0.04 ppl, but the rows below cannot train stably without it. So interestingly, you basically need a learnable W0 to make this thing effective instead of initializing with zeros. And the other things reduce it slightly, so we'll just go through them over here. You can instantiate F to either be an MLP. They note the MLP is like a normal transformer, so it would be a 4 times projection and then back down. Or you can have it just be a normal square matrix W. Both of them work and both of them are stable. And then you have a learnable eta. So remember, eta was our learning rate, and you can have the outer loop learn the inner loop's learning rate, as mentioned here. And you can do that with a neural network. So another thing to add. And then they also, you basically have to pick a backbone. So what backbone do you want to replace the attention with? So in a transformer, you would replace the self-attention with this, and in Mamba, you would replace the Mamba part with this here. So they pick the Mamba architecture. Interestingly, they mention below that picking the Mamba architecture was better than picking the transformer architecture, and we'll see that in a sec. So they do a bunch of experiments. This is on the pile, and they show flops flops by perplexity. I feel like this may hide some things, I don't know, but they choose flops by perplexity like most papers do. I'm not a big fan of flops, but they pick that because, I mean, that's what most people do. But they measure how the performance, or the performance versus a transformer, Mamba, and their method with either a linear projection, so the square W, the MLP, so the update rule in the hidden state as either a square W or an MLP, and using the Mamba backbone or transformer backbone, T. I mean, all of them are about the same here. This is on the pile 2K. Whenever you go to the pile 8K, the transformer requires more flops here, but the perplexity is a little bit lower. They measure about the same here, so that's that. Here we can see a bigger difference. The transformer uses way more flops, and this is on the log scale, so yeah, this is a big jump for a large corpus of text, so 32,000. And the Mamba, their version of the model with Mamba, uses the least amount of flops while being very performant in terms of perplexity. So yeah, there we go. That's it. That's on large scale books. They have some scaling laws here, which I don't think is that big of a deal. Oh, they have this here. So if we look here, this was the graph they showed above. If we look at the Mamba and architecture the Mamba and transformer architectures, like these kind of level off before this model does, which is pretty interesting. That means that this model uses in-context learning better, even though this is a hidden state, or even though this is an RNN using a hidden state. And that means we can compress information into a hidden state just fine. So that's pretty interesting to see. So yeah, this uses in-context learning better than a transformer, which literally has all the context at its disposal, which is really quite cool. I think this may be on the pile, so it'll be interesting to see how this works on other tasks as well. Yeah, more tests and stuff. Yeah, but that is the model. I think this method is really cool, and I am really curious to see, does this scale? Does this work on actual tasks rather than the kind of normal ones that you would normally test that they showed? And can this be made better? Like, I think if we look at the architecture down here, I think these are vectors. But if you look at, say, Mamba, it uses a matrix for the hidden state. This uses a vector as the hidden state. I wonder if it can be made more expressive by using a hidden state that is square rather than a vector. So just a thought. But yeah, this is a really exciting thing to see. Something new, something different. I'm very curious to see how this actually performs.